How does fracture toughness stop brittle materials from breaking? Imagine a tiny crack forming in a ceramic plate. Without any resistance, that crack could spread quickly and shatter the whole thing. But in some materials, there's a built-in defense that prevents this from happening so easily. That defense is called fracture toughness. It's a property that tells us how well a material can resist crack growth. Brittle materials like ceramics and some hard metals tend to break suddenly with very little warning. They don't bend or stretch much before breaking, so cracks can grow rapidly once they start. Fracture toughness measures how much stress or energy a crack can handle before it starts to grow uncontrollably. When a material has high fracture toughness, it can tolerate larger cracks or higher stress concentrations without breaking apart. At the microscopic level, fracture toughness involves mechanisms that slow down or stop crack growth. One of these is intrinsic toughening, which happens right at the crack tip. Even in brittle materials, some resistance to damage exists because of how the material's tiny structures, like grains or boundaries, interact. These interactions can make it harder for the crack to advance. The other mechanism is extrinsic toughening. This occurs behind or at the crack tip and includes things like crack bridging. Imagine fibers or grains that remains unbroken across the crack faces, holding them together and reducing the force that drives the crack forward. These mechanisms act like tiny barriers, making it more difficult for the crack to grow and cause failure. Temperature and the material's microstructure also influence fracture toughness. For example, metals become more brittle at low temperatures because their ability to deform plastically is reduced. This means cracks can grow more easily, increasing the risk of sudden fracture. The arrangement of grains and boundaries can either block or help cracks spread, affecting the toughness. Understanding fracture toughness helps engineers design safer, more durable products. They can choose materials with higher toughness, improve microstructures, or apply treatments that increase resistance to crack growth. This way, they prevent unexpected failures and extend the life of components. In simple terms, fracture toughness acts like a shield that stops cracks from growing too fast. It requires a certain amount of stress or crack size before failure can happen. This property is vital for preventing sudden, catastrophic breaks in brittle materials, giving us a better chance to catch problems early and avoid disaster.